In this lecture, we're going to talk about laboratory mathematics. So, laboratory mathematics, why do we care? So, the performance of accurate and precise chemical tests is a critical part of providing quality laboratory data and improving patient health outcomes. So, errors in calculations that we may perform can affect the preparations of reagents and standards, which could then affect the assay results. And also, there are calculations that we do with the patient results, even if everything was prepared and run correctly in the assay, that can affect the reporting of the patient results. So, all the math that we do, it's very critical that we do it correctly so that the patient's results are not affected, because these errors can be life-threatening to the patients. So in this lecture, we're going to discuss some definitions, how to do rounding in the clinical lab, which is different than what you're used to in your math class, the metric and systems, international systems of measurement, atomic mass, moles, percent concentrations, parts per million and parts per billion, molarity, molality, and normality. And these are all ways to describe concentrations of a solution, as well as hydrates and very briefly dilutions, since we will be covering those in significantly more detail as the semester progresses. All right, so some critical definitions is first, a chemical is in its most basic form an element or something composed of elements, like a molecule, that has a specific molecular composition and can be produced by or used during a natural chemical process. So even water is considered a chemical. So a reagent denotes any chemical compound or solution that's used in clinical assays. So it's important to note that water is a reagent. It's not just water, it's a reagent. We have different grades of water too. So in the laboratory, these chemicals make up the reagents, which are then used in assays. So when we're making solutions, we have a solute, which is the minor component in a solution that's dissolved in your solvent. So that's something like sodium chloride or glucose. And you also have your solvent, which is the liquid, that part of your solution in which the solute is dissolved in to form the solution. So that could be something like water or ethanol or isopropyl alcohol, saline, all manner of things. So we're going to talk about rounding really quickly. So rounding in the clinical lab is different than what we do in your standard mathematical class. And that's because we have these specific rules in order to avoid introducing positive bias to the results. So the reason why we round in the first place is to avoid overstating the confidence that we have in our test results. So if you bring it out to 5 decimal places, then it makes it seem like we are super confident to 5 decimal places that this is the right answer, when in reality, we might only be confident to 1 decimal place. So we round in order to show our confidence in the precision of that test result. And then we have different rounding rules in order to prevent positive bias. Because if we always rounded up when a number ended 5, then all those numbers that are on the border would always be rounded up, and that would introduce a positive bias. So these rules that we use in the clinical lab is, number one, to determine how sensitive or precise do you think the method is. So where's the confidence is in that number. So for an example, the number that came off of immediately out of our calculator was 3.155. We're only confident to 1 decimal place, so we're going to round that to 3.2. And a lot of times the reference range for your laboratory assay will give you the confidence that you have in the assay. So for example, albumin has a reference range of 3.5 to 5.3 milligrams per deciliter. So we would be rounding to 1 decimal place. Okay, so in terms of rounding rules, these are ones that you should be familiar with. If the number immediately to the right of the last retained number, which is the one underlined right here, this 6, is more than 5, you're going to add 1 to the retained number. So you're going to round up. So 3.165 becomes 3.2. This is what you should be used to doing in math class. For rule 3, if the number immediately to the right of the last retained number is less than 5, you don't change anything, you just keep it as is. So 3.143 goes to 3.1. So this should be pretty standard of what you're used to in math class. It's when we get to rule number 4 that it's kind of different for clinical lab science, so that we don't introduce positive bias. So if the number immediately to the right of that last retained number is 5, we don't know if that 5 is technically like a high 5 or a low 5, because we don't know how precise our method is. So the way to prevent introducing positive bias is to always round to the even number. So for this example, 3.15 is actually going to get round to 3.2 because 2 is even. Whereas 3.25 in regular math, you probably be used to rounding that to 3.3. This is also going to be rounded to 3.2 because the 2 is even and the 3.3 would be odd. So by doing this, whenever you have these numbers that are right on the 5 of whether you should round up or down, when you always round to the even number, you are avoiding creating positive bias by sometimes some numbers get rounded down, sometimes some numbers get rounded up, so it all evens out in the long run. All right, so now we're going to describe solutions in mathematical terms. So there are systems of measurement in place to help describe units. So the metric system uses the base unit of a gram for mass, whereas the SI system uses a kilogram. That's kind of one of their main differences. The metric system uses a meter, so does the SI system. And then in the metric system, the volume is a liter. It's also a liter in the SI system, but the liter is actually derived from meters cubed, whereas in the metric system, the liter is its own independent unit, and it's not derived from anything. They both use time in seconds, and then the metric system uses temperature in Celsius, and the SI system uses temperature in kelvins. Usually we're going to be dealing with the metric system, and it's important to note that 1 deciliter equals 100 milliliters. You should just memorize that and become one with that number, because it will save you a lot of headache when you're doing calculations in the clinical lab, because a lot of times we're going to want to be in deciliters. So the metric system, these are, the base unit is the liter, gram, or meter. So that would have 10 to the 0, which is actually 1. And then it has different measurements up from there. So you have deca, hecto, kilo, which is one you should be familiar with, which is 10 to the 3rd or 1,000 grams, meters, or liters. 10 to the 6th is a mega, and 10 to the 9th is a giga. And then for the clinical lab, a lot of times we're going to be dealing in these smaller numbers, so things that are smaller than the base unit. So deciliters, milliliters, microliters, nanoliters, those are all going to be used very commonly in the clinical lab, because when you're dealing with analytes in the body, they're not in super high concentrations. So be familiar with how to convert between these, and there is information in your lab math packet on how to do that. All right, so there are different ways to express concentration. So we have percent solutions, which are actually parts per 100. You also have parts per million and parts per billion, which is really good for very dilute substances. Molarity, molality, and normality, and we'll talk about each of these individually as we continue on. So percent solutions are parts per 100. This is where you take your part, or your solute, over the total amount of the solution times 100 to get a percentage. So this percent solutions is commonly used in SOC reagents. For example, 91% isopropyl alcohol is a percent solution. So there's weight percent, where you have the weight of the solute over the weight of the solution times 100. You have a volume percent, which is the volume of the solute over the volume of the solution, and this is total solution, times 100. And then you have a weight volume percent, where you have the weight of the solute, say you weighed out 5 grams of sodium chloride, and the volume, the final volume of the solution, times 100. So the weight percent is commonly used to indicate the concentration of commercial aqueous reagents. For example, 70% nitric acid contains 70 grams of nitric acid per 100 grams of solution. You also have volume percents that are used to indicate the concentration of a solution that's prepared by dilution with another liquid. So for example, a 5% volume by volume percent methanol contains 5 milliliters of pure methanol per 100 milliliters of solution. And then you have the weight volume percent, which is used to indicate the composition of aqueous solutions that were made with solid reagents like salt. So if you have a 5% weight volume solution of sodium chloride, that means you weighed 5 grams of pure salt, and then that is diluted to 100 milliliters of solution. So you're not just dumping in 100 milliliters of water into this 5 grams of salt, because you have to take into account the volume displacement of the salt, because 5 grams is quite a big mass. So you would weigh out your 5 grams, put it in a beaker, and then QS, or fill to a quantity sufficient to 100 milliliters. So we're going to talk about some example calculations. So this one wants you to calculate the weight volume percent of a solution prepared by dissolving 8.95 grams of sodium chloride in enough water to make 50 milliliters of solution. So to do this, we're going to take a look at the units that we already have. We have grams and milliliters, so that is ideal. So we're going to do our grams of sodium chloride over 50 milliliters of solution times 100, and that will give us 17.9% weight volume solution. Now another one. So what weight of glucose is needed to prepare 150 milliliters of a 10% weight volume solution? So for this, we have our base calculation where you have weight of the solute over 100 mLs, and then you want to make 150 mLs, so this will be your X. So we know that we want a 10% weight volume, so we do 10 grams over 100 milliliters, because that's by definition a 10% weight volume solution. We want to make 150, so we multiply by 150 to get 15 grams. That's one way to set this up. I personally don't really like doing it this way. I'll show you the way I like. So the way I like to do it is to actually do a ratio. So where you have 10 grams of your glucose over your 100 milliliters of solute, so that's your 10% weight volume solution by definition. And then you do, okay, how much glucose do I need to make 150 milliliters? And then you cross multiply and solve for X and get 15 grams. I just like it better this way. It works better in my brain. If you like the other way, that's fine, whichever way works for you. So our next question is to make 300 grams of a 20% weight by weight aqueous solution of sodium chloride. So first we need to calculate the weight of solute or sodium chloride that we need. So to do that, we want 20% weight by weight. So 20 grams over 100 grams times 300 grams. Once again, you could do the ratio cross multiply thing from the previous slide, and you get 60 grams of sodium chloride that's needed. But now we have 60 grams of sodium chloride that we added, but we only want 300 total grams. So we need to subtract out that 60 grams from the 300 grams of solution. So what we need to add is to add 240 grams of water to that 60 grams of sodium chloride. All right, so the next question is how much ethanol is needed to prepare 150 milliliters of a 15% volume by volume solution, and how do you prepare the solution? So first we're going to calculate how much solute we need to make a 15% volume by volume solution. So we have 15 mLs over 100 mLs times 150. You could do the ratio and cross multiply and solve for X. And you get 22.5 milliliters of ethanol is what's needed to make 150 milliliters of this solution. And then you need to subtract out this volume of ethanol for how much solvent you need to add, because we have to take into account that this is a contributing member of the total solution volume. So we have 150 mLs of solution minus the 22.5 mLs of ethanol. So we need to add about 127.5 milliliters of solvent. So you mix those together. In reality, alcohol is actually kind of funny because when you add alcohol and water together, there's actually a molecular rearrangement that happens that actually causes the final volume to be lower than what you predicted. So what you would do in reality for this is you would add your 22.5 mLs of ethanol, and then you would QS, or fill to a quantity sufficient to get to 150 mLs. This could be done in a volumetric flask, 150 ml volumetric flask. Because if you just added the 127.5 milliliters of water, you'd actually underestimate and not make enough. You wouldn't make 150 mLs of solution in total. thanks to molecular rearrangement. All right, so now we're going to talk about parts per million and parts per billion. So parts per million is the number of parts of solute per 1 million parts of total solution. So this is commonly seen with like chlorine. So we have 5 parts per million of chlorine. That's equivalent to saying there's 5 grams of chlorine in 1 million grams of solution. Or you'd have 5 milligrams of chlorine in 1 million milligrams of solution, or 5 pounds of chlorine in 1 million pounds of solution. So it's just 1 part of your solute in 1 million parts of your total. And this doesn't have to be a solution. This can actually be like a solid mixture. So it could be like a solid. It doesn't have to be like water or something. It doesn't have to be a liquid. It can be another compound. So parts per billion is the number of parts of solute per billion parts of solution. So it's super dilute. So parts per billion and parts per million is a convenient way to express the concentrations of very dilute solutions or mixtures in terms of their volume or mass. This is not related to moles. This is just purely based on volume or mass. So a handy rule to calculate parts per million is to remember that 1 part per million is 1 milligram per liter in solution, or 1 milligram per kilogram in a mixture. And I like this diagram because it shows like this is 1 million parts and it's just this one tiny little part. It's like a little speck. So 1 in 1 million chance. And these are some other ways that parts per billion and parts per million can be expressed using weight, volume, and volume. All right, so to calculate parts per million or parts per billion, you're going to take the mass of your solute over the mass of your solution and then multiply it by your base for million or billion. So for millions, that would be 10 to the 6th, and for billions, that would be 10 to the 9th. And that will get you into concentrations of parts per million or parts per billion. All right, so now we're going to do some practice calculations with parts per million. So for any solute, it's important to remember that 1 microgram is it's 1 microgram per milliliter is the same as 1 part per million. So for our example question down here, we have a solution of sodium chloride. You have 500 mLs of the solution, and each of these stars represents 1 milligram of sodium chloride. So we want to calculate the concentration of sodium chloride in the beaker expressed as parts per million, and then we also want to know the total amount of sodium chloride in the beaker. So to do this, we're going to count how many stars we have. We have 15 stars, so we have 15 milligrams of sodium chloride. So that's how much total is in the beaker. And then we're going to make a ratio of the amount of sodium chloride, or the stars, to the volume that we have, which is 500 milliliters. And we get, so this is just simply dividing them, we get 0.03 milligrams per milliliter, but we need to be in micrograms per milliliter for parts per million. So we're going to convert that milligrams to micrograms by multiplying by 1,000. And these milligram units will cancel out each other, and you'll end up with micrograms per milliliter, and that will be 30 micrograms per milliliter, or that is equivalent to saying 30 parts per million of sodium chloride in our solution. All right, so now we're going to talk about the atomic mass. This defines the relative mass of an element's atom. So the mass of the carbon isotope, or the 12 carbon isotope, is defined as 12 mass exactly. So everything in the atomic mass is referenced back to this carbon atom. And 1/12 of this mass is called a unified atomic mass unit, or a Dalton. And every other element is related back to that carbon unit. So for example, hydrogen has an atomic mass of 1.0079. Carbon is 12.011, because that takes into account the other isotopes of carbon, like 13, which would be slightly heavier. So these are average. Aluminum's 26.9815, iron, cadmium, uranium. And so that's the official definition of atomic mass. You can also kind of reference this back to the relative atomic mass compared to 1 atom of hydrogen, and that should be 1 atom of hydrogen should be about 1. So you can relate it back to the atomic weight of other atoms back to hydrogen, but the official definition is relating it back to that 12 carbon isotope. All right, so when you look at a periodic table, on the periodic table, it will tell you the atomic weight of every element on the table, which is located right here on this particular one. And that will help you figure out the moles of your atom or molecule. So a mole is related to Avogadro's number, which is 6.022 times 10 to the 23rd particles of any kind. So just particles. So that particle could be an atom, that particle could be a molecule. If the particles are atoms, then that weight of 1 mole, or the mole weight, is called the atomic weight, which is in grams per mole. Or if the particles are molecules, the weight of 1 mole is called the molecular weight, which is also in grams per mole. And to calculate moles, you have grams over the molecular weight of the atom or molecule. So we can use the moles to calculate the molarity of a solution. So the number of moles of a solute, like sodium chloride, that are dissolved per liter of total solution. And that is the molarity, which is abbreviated as a capital M. So the mole is related to Avogadro's number. And then for compounds, the atomic weight is the combined weight of the individual atoms. And that's what's used to calculate the molecular weight. So for example, if you had sodium and chloride, you would look on the periodic table, look up the atomic weight of sodium and the atomic weight of chloride, and add the two together, and that would be your molecular weight for sodium chloride. So when you're solving molarity problems, there's a few general steps to do. First, you want to identify the units of the desired answer. So what are you trying to get to? And then write them on the left side of the equation, so you have that in mind of, okay, I'm trying to get to micrograms per milliliter, or so you know what unit you're trying to get to. And then you want to write all the given numbers that you were given. So for example, if you were given weight and volume, you want to write those down. And then you have the units and ratio forms on the right side of the equation, and you add additional units in ratio form to enable cancellation of all those units except the ones that are desired in the answer. And what's nice about these ratios is that they don't change the overall answer. They're just basically like multiplying by 1. So for example, 1,000 milligrams divided by 1 gram, that equals 1. But it helps you change the units to what you want. So even though you're multiplying by 1,000, it's mathematically the same as multiplying by 1. So then you're going to perform the calculation, and we'll show you some examples. All right, so for this example, you want to calculate the molarity of a solution of sodium chloride containing 87 grams per liter of solution. So first thing we want to do is put our desired units on the left side. So we want molarity, which is moles per liter. There, moles per liter, got it. And then we want to write all the given units that we have to the right. So we were given 87 grams per liter. So we'll write that down. And then we want to cancel out and multiply by ratios to cancel out the units we don't want to get to the units that we do want. So for this, we have 87 grams per liter. It's important to always put down, write down the sodium chloride each time it is, because as these questions get more complicated, you're going to want that information so you don't get lost in your calculation. Also, from a grading standpoint, it allows me a much easier job to figure out what you were doing and what you were thinking and to award partial credit. So always write down everything with units and what substance it relates to. So for this one, you have 87 grams of sodium chloride over 1 liter of solution. And then we're going to multiply by the reciprocal of the molecular weight so that our grams will cancel out. So because we're multiplying by the reciprocal, grams is on the bottom, so it will cancel out with the one that's over here on the top. And then mole and liter will remain. I always like to physically cross everything out and then look through the equation before I solve it to make sure that I haven't missed getting rid of any units that I needed to, and that I don't need, and that I will end up in the units that I think I'm going to end up in. Because right now I can see that I've canceled out grams and that I have moles and liter remaining, And since that is what I want, I'm good to go. So I multiply 87 by 1, and then I divide by 1 times 58.5. So when I'm actually putting this in the calculator, I do all of these that are on top, multiply all those together that are on top, and then divide, and then I put in what everything is on the bottom. If you have a scientific calculator where you can do parentheses, it's much easier. But if you don't, you have a simple calculator, multiply all the things that are on top, write it down, multiply all the things that are on bottom, write it down, and then divide them appropriately. All right, so when we actually solve this, we get 1.49 moles of sodium chloride per liter, which is actually 1.49 molarity of sodium chloride. All right, so for our next problem, how many grams of sodium hydroxide are contained in 500 milliliters of a 4 molar solution? So we can put our desired units on the left-hand side. So we want to know how many grams of sodium chloride or sodium hydroxide are in this solution. So that's the question. And then we want to write what we do have. So we have molarity, 4 molar solution, and 500 mLs. So this is the molarity, 4 moles of sodium hydroxide over 1 liter of solution. And then 500 milliliters over here. You could do that right here. I just like doing it at the end because I don't like having all these divider things separated. It's just cosmetic, it doesn't matter. I just like doing it at the end. You could totally do it right there. So we're going to cancel out our moles first. I like to work on the top first, getting the top part to where I want it to be, and then I work on the bottom. So for 4 moles, I will multiply by the molecular weight of sodium hydroxide, which is 40 grams per mole. So our moles is going to cancel. Right now I have grams, which is what I want, so I'm not going to mess with that. And then right now I have liters of solution, but I don't need the liters at the end, so I need to do something to get rid of it. So I'm going to multiply by, this is essentially by multiplying by 1, because there's 1,000 milliliters in 1 liter. So, and then times my volume of solution that I actually have, which is 500 milliliters. So at this point, the liters have canceled out and the milliliters have canceled out. So I'm left with nothing but grams at the end, and then I can solve for this equation, and I get 80 grams of sodium hydroxide is in the 500 milliliters of a 4 molar solution. All right, so for our next question, we're going to a solution contains 3.5 grams of hydrochloric acid in 1 liter of solution. So how many millimoles does it contain per liter? So basically, what's its millimolarity? So we're going to put our desired units on the left-hand side, which is millimoles per liter. And then we are going to put what we do know, which is 3.5 grams in 1 liter of solution, and then cancel out grams by multiplying by the molecular weight, the reciprocal of the molecular weight of hydrochloric acid. And then we're going to get it into millimoles, because right now it's in moles at this step. So we basically multiply by 1 in order to convert it to millimolars, because there's 1,000 millimoles in 1 mole. And then we can solve for that. So right now at the end of this, we have liters that isn't crossed off, and we have millimoles that isn't crossed off. So this will give us 95.9 millimoles per liter of hydrochloric acid in our solution. All right, so that was molarity. Now we're going to talk about molality. So molality is the number of moles of solute that are dissolved per kilogram of solvent. So molarity was the volume of the solution in liters, whereas molality is actually divided by the mass of the solvent, not the solution, in kilograms. So molality is a weight measurement, and it's independent of temperature variations. So because it's independent of temperature variations, this actually makes it a more accurate measurement of concentration than molarity, but it's not really convenient to use. So it's not used very often. So usually volume of a solution is dependent on the ambient temperature and pressure. We've all known that if you leave a water bottle with a straw in a hot car, it will leak, because as the temperature increases, that volume expands and the liquid come out of the straw. Same with airplanes. If you have a straw cup, like a Contigo water bottle that is closed on an airplane, and then you open it once you've reached your flying altitude, you're likely to get sprayed in the face. That's because that increased pressure the change in pressure will cause the volume of your solution to change. So molality is nice because it's sheerly just the mass of the solvent. So you can weigh this out on a scale and add it to your weighed out solute, and you've got your molality. You don't have to take into account volume displacement or anything like that, or expansion of solution. It's convenient, or molecular rearrangement. So when we calculate molality, so our example is, what is the molality of a solution if 127 grams of sodium chloride, which has a molecular weight of 58.5 grams per mole, were dissolved in 1,000 grams of distilled water? So this is our weighed out solvent, which is 1,000 grams or 1 kilogram. And we're adding 127 grams of sodium chloride. So what do we want? We want molality, which is moles per kilogram. And we want to write what we do know. We know that we have 127 grams of sodium chloride. We know that we have 1,000 grams of water. So we need to get moles out of this. So we need to multiply by the reciprocal of the molecular weight, so that grams of sodium chloride cancels out and we're left with moles on the top, which is one of the units that we need remaining. And then we want to convert that grams to kilogram. This isn't really necessary for this question because it's already 1,000 grams of water. But say it was 500, you would need to, it would be helpful to do this step so that you make sure that you're in the right units. So we now have kilograms and moles remaining. So that will give us, when we solve it, 2.17 moles per kilogram of sodium chloride, or 2.17 molal. So molality can also be represented by a lowercase m, but that's kind of fallen out of favor as an abbreviation, and molal is what is recommended as the abbreviation for molality, especially since capital M's and lowercase m's, it can be difficult to tell them apart. And then you might confuse molarity and molality later down the line because you can't remember if you wrote a lowercase or an uppercase m. All right, so when you're making solutions, when you're actually physically in the lab, you want to add the solute either by volume or by weight, and then QS or fill to the line with the solvent to the final volume. And I see this problem a lot when students are writing out, when they're answering questions like, how would you prepare this solution after they've done all their calculations? They're like, oh, I had to add 100 milliliters of water when I want 100 milliliters total volume at the end, because they're not taking into account the volume displacement of their solute. So when you're actually making a solution, you want to weigh out or measure by volume your solute, and then QS or fill to the line with your solvent. So that way you take into account the volume displacement of your solute as well as any molecular rearrangement that your solute might have in the solvent. Because as we discussed earlier, alcohol, for example, when you mix it with water, it actually has a molecular rearrangement that will cause it to kind of condense, and it will take up less space than you think it will. So you would, if you just straight up added your water to the solution, you would not make enough. So that's why you need to QS to your final volume to prevent those errors from happening. So the exception to this rule is molality, because molality-based solutions are made by weighing the solvent independent of any sort of volume displacement caused by the solute. So for molality, you can just straight up weigh your solvent because that's the way that equation is designed. But for everything else, you need to QS to your final volume. All right, so now we're going to talk about normality. This is another expression of concentration. You're probably like, oh my goodness, there's another one. Yes, there's another one, but this is kind of the last one in terms of concentration. So it's very similar to molarity, except that the concentration is based on equivalent weight instead of molecular weight. And you're probably like, what is equivalent weight? So equivalent weight is defined as the mass of an element or compound that will combine with or replace 1 mole of hydrogen. So basically it's equivalenting, making everything equivalent to hydrogen is essentially what it's doing. So the equivalent weight is dependent on the total charge of the ion or the valence of the element. So your equivalent weight is your molecular weight divided by the valence. So for example, sodium has a single charge, so it has a valence of 1, whereas calcium has a charge of 2+, so it has a valence of 2, because you could, 2 hydrogens would be needed to replace 1 calcium in terms of charge. So in terms of determining the valence and the equivalent weight, if your compound is an acid, their equivalent weight is the quantity of substance that contains 1 replaceable hydrogen. So acids have hydrogens, right? So for hydrochloric acid, you have 1 hydrogen, so it has a valence of 1. Sulfuric acid has 2 hydrogens, so it has a valence of 2. So then you take your molecular weight. So for this example, we have sulfuric acid, which has a molecular weight of 98.08 grams per mole. And you divide that by your valence, which is 2, and you get an equivalent weight of 49.04 equivalents per mole. So usually when you're doing these calculations, you're not going to calculate this separately. You're just going to do it as part of the longer equation. So, but this is how it works in the equation. So if your compound is a base or a salt, then the equivalent weight is the quantity of a substance that will react with 1 replaceable hydrogen. So for sodium hydroxide, that sodium can be replaced by a hydrogen. So the valence is 1. Whereas with aluminum hydroxide, the valence is 3 because it would take 3 hydrogens to bind to that many hydroxyls. So when we calculate normality, we're going to do some examples. So what's the normality of a solution that contains 150 grams of sodium chloride, which has a molecular weight of 58.5 grams per mole per liter? So we're once again going to put our desired units on the left-hand side. So in this case, it's equivalents per liter. That is what a normality unit is. So molarity was moles per liter. Normality is equivalents per liter, or equivalent weight per liter. And then we're going to write out what we do know, which is 150 grams per liter of solution. And then we're going to multiply. I like to get rid of grams and get it into moles. So get rid of grams and you get by multiplying by the reciprocal of the molecular weight. And then you have moles remaining. So to get rid of moles and to get it into equivalents, you look at what is the valence of sodium chloride. So how many hydrogens could bind in this equation in this molecule if we popped off the sodium, which is 1. So we have 1 equivalent of sodium chloride is the same as 1 mole of sodium chloride. So we solve that and we get equivalents per liter, or 2.56 equivalents per liter. And for some reason, that is wrong, but 2.56 normality. I don't know why that number changed. That's what happens. So if this was calcium chloride, it would actually be 2 equivalents per mole, and we'd end up with half the normality, or twice the normality. All right, so now we're going to look at calculating the normality of a solution containing 75 grams of barium hydroxyl. So that has a molecular weight of 171 grams per mole and 850 milliliters of solution. So we're going to put the desired units on the left, which is equivalents per liter. And then put what we do know, which is 75 grams of our barium hydroxyl in 850 milliliters of solution. So this is what we know already. We do know the molecular weight. I will not always give you the molecular weight. You will have a periodic table and you'll have to calculate the molecular weight. So that is something to be aware of, is how to calculate the molecular weight from a chemical formula. So we multiply by the reciprocal of the molecular weight to cancel out grams. And then we multiply by this equivalent to mole ratio, which in this case, this has 2 equivalents because we could bind 2 hydrogens in place of this barium. And then we need to get rid of the milliliters, so don't forget that. So this is why it's helpful to look back before you do your equation to go, am I in the right unit? So I needed liters right now. If I stopped right here, I would only have milliliters, which would be wrong. So I need to do an additional conversion to get rid of the milliliters. So I do that by multiplying 1,000 milliliters over 1 liter, and then I can solve my equation, and I get 1.03 equivalents per liter, or 1.03 normality. All right, so one thing that's cool about plasma is that the equivalents, which are based on charge, of cations and anions in your plasma are actually equal. So your body is net neutral at any given point, unless something's gone out of whack. But even it's still neutral then, just the ratio of these anions and cations changes. But you can see that the actual charge here is the same for the anions and the cations. So you'll often see, and when you learn about clinical chemistry next semester, that the major electrolytes such as sodium, potassium, and chloride are actually reported in milliequivalents per liter rather than millimoles per liter. But millimoles per liter and milliequivalents per liter are actually the same for sodium, potassium, and chloride, or anything that only has one charge, whether that's negative or positive. So, fun fact. All right, so for hydrates, the chemicals are often manufactured with water attached to each molecule of salt. So that's the water of hydration. So for calcium chloride, that has has 2 waters attached to it, and it's referenced with this little dot times with the molecules of water. So for depending on the substance, that could be like 1, it could be 7, and you need to account for the water in your calculations when you're making reagents. So for example, the molecular weight of calcium chloride by itself is 110.98 grams per mole. Molecular weight of water is 18.02 grams per mole. So the molecular weight of this hydrated calcium chloride is 110.98 grams per mole plus 2 times the molecular weight of water. So if it was 5, you multiply by 5. You just want to make sure that you're accounting for each molecule of water. And you add those up and you get 147.02 grams per mole of hydrated calcium chloride. So the easiest way to approach these hydrate calculations is to use a ratio proportion setup to complete the problem, which I will show you. All right, so for this question, you want to calculate the number of grams required to prepare 400 milliliters of a 0.5 normal solution of sodium chloride, but unfortunately, you only have a hydrated form of sodium chloride. So what are you to do? So the first thing you want to do is figure out how much sodium chloride that's not hydrated would you need to make this solution. So in a perfect world, if you had calcium chloride, how much would you need? So we will do that. So we put what we want on the left. We put what we have, which is 0.5 equivalents per liter, which is our normality that we want over here, times the 2 equivalents in calcium chloride times the molecular weight of calcium chloride. And then you need to convert into milliliters because you want 400 milliliters at the end here. I forgot to cancel out these units. So milliliters will cancel here, and liters will cancel here. Equivalents will also cancel, and you're going to end up with only grams at the end. So you're going to get 11.1 grams of calcium chloride is what you need to make a 0.5 normal solution. But you only have calcium hydrate, so now you're going to do a ratio. So you take 110.98, which is the molecular weight of calcium chloride, of the anhydrous calcium chloride, over the 147.02, which is the molecular weight of your hydrated calcium chloride. You make a ratio where you have 11.1 grams of your calcium chloride that you need for your solution, and then you're going to solve for x. So you're going to cross multiply and solve for x, and you're going to end up needing 14.7 grams of calcium chloride, hydrated calcium chloride, to make this solution. And for this in particular, it is extremely important to label whether you're talking about calcium, the anhydrous or the hydrous calcium chloride, because it can get very confusing in terms of grading and for you when you're doing the problem. So always label whether it's the hydrous or the anhydrous. All right, so now the last thing we're going to talk about is dilutions. We're going to talk about these very briefly because we're going to go into these in way more detail in the first few weeks of lab. So in a dilution, water is added, and that will increase the volume, but it also decreases the concentration. So a way to calculate dilutions is using the equation V1C1 equals V2C2, where V1 equals the volume before dilution, C1 is the concentration before dilution, and V2 is the volume after dilution, and C2 is the concentration after dilution. In order to solve this, you need to know at least 3 of them so that you can solve for whichever one is remaining. And it's also important to note that the units must be the same on each side of the equation. So you can't have molarity over here and normality over here. Everything has to be in the same starting units before you do any solving. And whatever you're solving for is going to have the same units as its appropriate part over here. So if this was in liters, when we solve, V2 would also be in liters. All right, so just make sure all the units are lining up correctly and then they're starting the same. All right, so to do calculation, so this one wants us to calculate the concentration of a solution if we have 25 mLs of a 1.5 molar solution and it's diluted to 250 mLs. So we're going to fill in with what we know. So this is our equation that we're working off of, and which ones do we already have? So we have V1 equals 25, C1 equals 1.5. We have V2, which is our final volume, is 250. So the only thing we don't know right now is C2, and because C1 is in molarity, when we solve for it, C2 will also be in molarity. So we plug these into the equation and we solve for C2, and we end up with C2 equals 0.15 moles. But you see how everything else here only has one decimal, this only has one decimal place. We need to round. This is directly on 5. So we're going to round to 0.2. If this had been 0.25, we would have rounded to 0.2. So just making sure that when you're doing these equations that you're rounding appropriately according to our rules, and please wait to round until the last step so that you don't lose precision. So always round to the last step. All right, so that ends the lecture on some basic laboratory math. There's also the handout if you need more information, and then there's a practice assignment, as well as an assignment that you will turn in for grading.